Review part two. All right, so picking up right here on section 4 on your review sheet, rates of reactions. So a rate's talking about how fast something happens. And just in general, reactions are going to occur when molecules collide. So if we can increase the rate of collisions, then we're going to increase the rate of reactions because that's what reactions need. Reactions need collisions. We need to make more collisions. So we can increase a lot of things in order to make more collisions. We can increase the concentration, which means we've got more stuff, right? We can increase the heat or the temperature so that that's going to cause things to be moving around more. If it's a gas in particular, we could increase, it's really bad writing, so we're going to increase the pressure. We could also change the surface area by crushing stuff up. That typically is going to make it react a little bit faster because there's more surface area. And lastly, we could speed things up by adding a catalyst. Bad spelling again. So let me try that again. Catalyst. So all of those are ways that we can generally speed up the reaction rate of something. Generally, reactions don't happen without some kind of a push, which is what's going to allow it to get over the hump on the graph when we represent what's going on with a reaction. Remember that hump on this thing is what we call the activation energy. It's the kind of the energy needed to get it going. And again, on the period table, the graph that we have here, it's going to be represented by a little hump that we have right here. So our reactants are going to start out here. In order to get products down here, we need to give them a little bit of a push, like when we would light the Cheeto to get it going. Otherwise, we don't light the Cheeto, it just stays Cheeto. It just kind of hangs out right there. Even though there's plenty of oxygen in the air, we need to give it a little push to get it going. So if we added a catalyst to our reaction, generally that's going to cause the hump on this thing to go down a little bit because it's going to reduce the activation energy, should make it a little bit easier to happen. An inhibitor, on the other hand, is going to raise the activation energy, make it a little bit harder for anything to happen. Right? And on this graph, if we wanted to decide if it's exothermic or endothermic, remember exo means out, endo means in. And so we're kind of just asking, is there heat going out? Is there heat going in? I often use the analogy of money as well, about thinking about this as saved up money, because if you've got potential, then it's stored. We can do some stuff with it. And if this is my bank account, then comparing the beginning to the end, my bank account has dropped. So I'm spending my money. In the terms of energy, we're not really spending money, but we're spending energy. So the energy is coming out of this. And so this is going to end up being an exothermic reaction because the bottom is lower than the beginning. Right? If we did an endothermic graph, that means we got energy coming into it, and if energy is coming into it, it's like saving or making more money. And we would expect, even if we had activation energy, we would have a little bit of a bump, and then eventually we would expect it to end up maybe plateauing. Not the perfect one here. But the main thing for us to recognize is that if it's an endothermic reaction, that we would need to go from a lower state of energy up to a higher state of energy because we're going to be gaining some energy. And in order for you to gain energy, it's got to come from somewhere else, and you would have to take it in. Part 5 on equilibrium, this was a little bit confusing for a lot of people when we had these reactions that were written out, and you're kind of asked to predict what happens to the reaction. And I thought a better way, in the class I used a balloon, but another way to think about this would be if you had an aquarium that had a divider in the middle that was not quite a divider, that water could actually go through it. So you might imagine if you started pouring water into the side's going to start filling up, but at the same time, some of it's going to start going into this other side. And particularly if you were adding them in, a whole bunch of this at once, maybe this side ends up being higher to begin with than the side over here. But you could also probably imagine that over time, whatever levels of water you had would end up leveling out on both sides, because since there's some holes over here, you wouldn't expect one side to have a higher level of water than the other one. Once everything was done, they're going to end up balancing out with one another. So that's the idea behind equilibrium, is that ultimately the water levels on each side are going to be the same, right? That they're going to be equal. And that's kind of like a chemical equation with equilibrium. So what I'm talking about here with equilibrium is when, instead of having this mesh, we've kind of got our arrows going in both ways, and we've got reactants on one side, we've got products on the other side. If we wanted to predict, because again, this is a reversible reaction that can go either way, Think about what would happen to your aquarium if you either added some stuff to one side or you took some stuff away. If we were at equilibrium and we added more stuff to the left-hand side, just like at the beginning, we would expect to get more stuff eventually into the right-hand side. We wouldn't expect, again, one side of the water to remain higher than the other one. They're ultimately going to balance each other out. So if you can envision what would happen to this aquarium, you should be able to figure out what's going to happen up here. So in other words, if I add something to the left side of this aquarium, it's going to push some of the water over to the right side of the aquarium as well. So in other words, if I add more substance, if heat was on this side, or if there was a gas and I'd added more pressure, it would push our equation and generally to be able to have more products in it. Conversely, think about what would happen if you removed some stuff. So if this was completely balanced out and you took a big cup and went through and pulled some water out of this side, dumped it out, we wouldn't expect the right-hand side to stay higher than the left-hand side. We would expect some of the water from the right-hand side to flow in and take up the space on the other side. So if we remove some things from the left-hand side, we would expect some things to get pushed over and shift back into that left-hand side. So just as when we added it, pushed it to the right-hand side, if we remove it, it's going to cause some stuff to go back into the left-hand side. So if you're given any kind of questions where you're asked to predict what's going to happen if you do something, perhaps try to use this analogy of water to say, well, if I add something to this side, what's going to happen? Well, it's generally going to push things over there. If I remove something from this side, it's generally going to cause something to move back to the other side. And it would be true the other side as well, right? If you added something over here, it's going to push some things over there. If I remove some water out of this side, we would expect water to move from the left back to the right. Okay. So that's a decent analogy. Again, if you had these substances, right? So if I added more A, I would expect to probably get more of these things over there. If I removed some B, I would expect to get more A and B made because the C and D products would kind of come back together to balance things out, just like if we removed the water that was there. Again, there is a practice sheet that we had in class to kind of go through an equation like this, and the answers for that will be posted in Google Classroom if you want to compare your answers to those. On part 6, again, this is our formula, Q equals MC delta T. We've been working on this a lot. The main thing with this is making sure you know what the letters mean. Q is for energy, M is for mass, specific heat is C, and a change in temperature is delta T. So in other words, the amount of energy that is needed to accomplish something depends on how much of it you got, what it is, and how much of a temperature change you made. Also keep in mind what the units are. Q is generally in joules, and that's if your specific heat is in joules. Sometimes your specific heat could be in calories. So that's one of the things I have down here. It says pay attention to the units. So for example, and this is on the back of your periodic table, if you need the specific heat of water and it's in joules, then we use the number 4.184. However, if it's in little c calories, we only use a 1. When we use this specific heat term, a reminder what specific heat is. It's not how hot it is. It's about how much energy it can take without changing its temperature. In general, what we're looking at is the higher the specific heat. Let me get that off the screen here. Close that out. All right. Generally, the higher the specific heat, the slower the temperature change is going to be. So the idea, like with water has a 4.184, and it's the number of joules effectively per calorie. In other words, excuse me, not calorie. Yeah, joules per calorie, or not calorie. Got my wrong C here. Apologize. 4.184 joules per degree Celsius. So in other words, it's the amount of energy that's needed to change the temperature of water. There's also a G down here, but I just use the J and the C to help me remember what they are. So the bigger this number is, that means it's more energy. More energy to do what? To change the temperature. So 4.184 versus 1, this requires way more energy to change the temperature compared to a 1. Therefore, this is going to heat more slowly or change temperatures more slowly than a 1. A 0.1 is going to change temperatures even more quickly because it needs very little energy to be able to change its temperature. Okay, so again, relationship here. Higher the energy, the slower we would expect the temperature to change. Water has one of the highest specific heats of most normal substances we come across, and it's again 4.184. To convert joules, if you do the math with all this and you get an answer in joules, if we want to go from joules to calories, we need to divide by 4.184. That'll change it into little c calories. If we want to further change that into nutritional calories, we will divide further, and we divide that by 1,000 because there are 1,000 big C, 1,000 little c calories in a big C calorie. When we have heating curves, a heating curve is going to show us an object, generally the way this graph looks, of going from a solid to a liquid. So if we wanted to label this, again, that's where our solid is, this is liquid, this is gas, and the flat lines are where there's going to be a phase change of one thing changing to another one. So if we have a solid to a liquid, we've got melting occurring. If we've got a liquid to a gas, we've got vaporization occurring. And we could also flip the graph around, and if we wanted to read it backwards, this line could also be when a gas turns into a liquid, which is condensation, or this line could also be when a liquid turns into a solid, which is freezing. One of the things about this graph to understand, hopefully, is that as time is passing, we're continually adding energy, but the energy doesn't always make the temperature go up. When the temperature is going up, that's going to be an increase in kinetic energy. But there's a couple places where the graph doesn't go up. So one of the things we should be able to kind of infer from this is that when ice is getting warmer, or when water is getting warmer, or when steam is getting warmer, the kinetic energy, the motion of those molecules is increasing. When melting is occurring or when vaporization is occurring, the temperature is not going up. All the additional energy is just overcoming the forces that are holding the solid together to loosen those up a little bit, so to speak, to turn them into a liquid. Right? So the way that this graph is, in order to go from solid to liquid to gas, it needs more energy. So we have to input energy into it. So the way that this graph looks, we've got energy going into it, so it ends up being endothermic. If we flip this graph around and made a mirror image so that it was looking as we were going from liquid to solid, think about when you're freezing something. In order to go from a liquid to a solid, you need to pull the energy out of it. So if we flipped it around, or if we said what energy is needed to go from a liquid to a solid, or from a gas to a liquid, or from a gas to a solid, we're having to remove energy from it. And when we remove energy, when energy comes out, that is better described as an exothermic situation or an exothermic reaction, if it were a reaction. The last part, Hess's law, just in summary, we'll try to keep it nice and short, and I'll do an example. Hess's law says if we can combine or simplify several equations into one, then the changes in heat of all of those equations that we combined should add up to the change in heat of the original, or the equation that we're trying to figure out. So in this example, this is how a question would look if you were asked to evaluate a Hess's law. We're trying to calculate the change in heat for this equation, and we know these other three equations, and we know the changes in heat for each of those three equations. So our goal is to say, can I make these three equations equal to the equation up here? So I can combine and I can kind of cancel out some things. If something is on the left side of an arrow and on the right side of the arrow and another one, we can kind of cancel it out. So for example, there's 6 hydrogens on the left and 6 hydrogens on the right. If we added all these things together, that would allow us to kind of cancel those out. You'll also notice that I've got 2 oxygens and 3 oxygens, so we can combine those together because they're both on the left side of the arrow. You can combine that up to 5 oxygens. You'll also notice there's 2 N2s on the left, and then there's 2 N2s on the right, which we can cancel those out. And then what we're left with is 4 NH3s, which is here, 5 oxygens, which is there, 4 NOs, which are there, 6 H2Os, which is there. So in essence, these two things are equal to one another. And if these two things are equal to one another, then all we have to do to get our answer is to add these up. Stick them in the calculator. Negative 361 plus 183.6 plus negative 1450.8. Hit the equal key. There's your answer. And whatever you get here is simply the answer to our problem. In most cases, even if you didn't quite understand this part over here, in most cases, you're going to get your answer simply by adding all of those numbers up right there. All right. Good luck. If you got any questions, let me know.